Alright, so what I'm going to talk about in this video is energy changes, but specifically talking about breaking bonds and making bonds. So what I'm going to start off with is this chemical reaction here, which is the reaction between methane, which is the gas from a gas tap. You set your gas tap, your Bunsen burner on fire, it reacts with oxygen, and it makes carbon dioxide. The carbons bond with the oxygens, and the hydrogens bond with the oxygens to form water. I'm going to balance this equation: 4 hydrogens, 2 H2Os, 1, 2, 3, 4 oxygens, and so 2 O2s on this side. So methane reacts with 2 O2s to make CO2 and H2O. Right, so what you're starting off with then is you start off, in any chemical reaction, you start off with your reactants with all the bonds that they've got. And then in chemistry, what basically happens in any chemistry is that you break all the bonds in the reactants, they jiggle themselves around a bit and they rearrange themselves in another form. And I often suggest this is rather like Lego. My lad's got a 3-in-1 Lego set where you can make a Lego truck and you can turn it into a Lego bulldozer. Alright, so if you've got a truck on one side, this is the truck. I don't know how to draw a truck. Oh well, it's a truck. And then you want to turn it into a Lego bulldozer. Why have they even done this? There you go, it's a bulldozer. If you want to turn it from truck into bulldozer, what do you have to do? Well, you have to break apart all the bricks over here and then build them up again, so stick them back together to turn them into this. So the processes involved in the Lego is breaking bonds between the bricks, and then you make new bonds between the bricks. Now, chemistry is incredibly similar. All right, you have bonds between carbons and hydrogens and oxygens. You have to snap all these first before you can turn them into something else. All right, so here's a little visual representation of this. I hope you all realise that when you set fire to methane, it gives out heat. So what type of reaction is this? That's right, it's exothermic. So the energy change here, delta H, or the energy, it might be used to call it energy change, or the enthalpy change, all words that you need to be familiar with, is going to be a negative number. It gives out a lot of heat, so it's going to be a negative number, whatever, negative 324, or whatever it might be. All right, it's going to give out heat. The reactants have got more energy than the products, and this released energy you feel is heat. Okay, because the heat as energy is released to the surroundings. Alright, so first thing to do here is I'm going to draw out these molecules in full. Now you get better at drawing out these sort of molecules later on in year 11, assuming we come back to school. So don't worry if this is the sticking point for you. Alright, this equation then is a balanced equation. So what I can see is you've got CH4. So I've drawn the carbon bonded to 4 hydrogens and 2 O2s. Now this big number 2 here means 2 lots of O2. Now an O2 molecule is an oxygen double bonded to another oxygen. That doesn't mean equals. So you've got 2 of them. Big number 2, 2 oxygens. So if I want to turn these into CO2 and H2O, what I've got to do is break all of these bonds first and then make new bonds. So carbon dioxide, CO2, looks like this, and H2O looks like this. But you'll notice I've got 2 H2Os. You've got to watch for that in the exam, which means that you're actually dealing with this. So in this chemical reaction, for this chemical reaction to happen, what you've got to do, well, firstly, you've got to put in a little bit of energy, and then you release a load of energy after. Remember, this energy is called the activation energy. So what you've got to do first is the energy that you put in is actually to break all the bonds. So I'm going to write that here, breaking bonds. You've got to put energy in to firstly break this bond, this bond, this bond, this bond, this bond, and this bond. And as you know, it's quite difficult to break something, apart from, if you saw in the last video, it's quite easy to break a pen. You've got to put energy in to break bonds. So I'm just going to write here, BB in, BB in. All right? Breaking bonds, you have to put energy in. Listen very carefully to this. Breaking bonds is an endothermic process. All right, that's a bit advanced that, but BB in. Just remember, BB in. Breaking bonds, energy in. So firstly, I'm going to break all of these bonds. So imagine now, I've snapped you. Well, what would I have? Well, if I snap all these 4, I'll have 4 hydrogens just floating around randomly, not joined to anything else. These 4 hydrogens were here. I'll have a carbon. I'll break this one and I'll have an O, O, and an O, and an O. In other words, you've got a selection of loose atoms, all separate. No molecules, there's no bonds anymore. So it's a bit like my lad with his truck. He breaks it apart, he's got a big pile of bricks. All right? Now we've got the job of sticking these bricks back together in their new arrangements, or sticking these atoms back together to make the products. Now here's the thing that isn't maybe that intuitive. When you stick two things together, energy is released. All right, I'll try and represent this with a pen. When you stick a lid on a pen, energy is released. Listen. Hear that? Sound energy is released. Hey, that's clever, isn't it? All right. It's not a really good analogy. But you just need to remember that when you make bonds, energy is given out. Oh, MB out. Making bonds, energy is given out. It's an exothermic process. Making bonds releases energy. Breaking bonds takes energy in. Making bonds releases energy or gives energy out. All right. So you're going to make this carbon will join to an oxygen and an oxygen. This one will join to this one and this one. An O will join to two H's, an O will join to two H's, and you'll make these products. So you'll make this bond, this bond, this bond, this bond, this bond, and this one. And you'll know where this is going because you'll have done some of these calculations. You can actually work out the energy required to break the bonds and the energy released making the bonds. But what I want to focus on here is what I just said, that last thing that I said, the precision that you need when describing these reactions. Because what the examiner can ask you is describe an exothermic reaction in terms of making and breaking bonds. All right. Describe an exothermic reaction in terms of making and breaking bonds. All right, now this is where my little BB in, MB out might be of use. So I hope you agree that this is an exothermic reaction. So all I've got to do is describe it. I'm not doing the calculation. That's coming in a minute. The calculation's actually really easy. All right, so when you look at this diagram, bond breaking in or MB out, which side of this diagram is bigger? Is it the BB in, which goes from here to here, or is it the MB out? Well, if it's an exothermic reaction, I hope you realise that this MB out side is bigger than the BB in side. All right? So how do you explain that? Well, the reason I've written BB in and MB out is just to help make sure that you hit all of the key points. If I start, describe an exothermic reaction. Why do exothermic reactions release heat? All right, so why do they release heat to the surroundings? Because more energy, this is how I always start this for exo and endo, because more energy is, right, this is the more side, more energy is out, is released, more energy is released, or I say given out, I could have said given out to go with out, more energy is released, so I've talked about the out, making bonds, more energy is released, given out, making bonds. I'm going to say given out. Released is really good, but I'm going to given out. I want to use the word out. More energy is given out making bonds, than is what word goes with in, taken in, okay, is taken in, breaking bonds. I'll just move that over to the side. More energy is given out making bonds than taken in breaking bonds. So the BB in and the MB out is making sure that you say those bits really carefully, because kids, students, even teachers get this wrong. They say more energy is, they talk about giving out and giving out on both sides, or taken in and taken in. It's not the case. All right. So I'm gonna show that again, but using an endothermic example. All right, so if you've got an endothermic reaction that looks like this, all right, what you do, firstly you break bonds, so you go BB in and then MB out. All right, why do endothermic reactions, so describe in terms of bonds, why endothermic reactions take heat from the surroundings. All right, or get cold or feel cold. And the question will be described in terms of bonds. Okay, so we're going to start it off. Because more energy, that's how you start it, more energy is. So, which one is more? This side is more. Because more energy is in, BB in. So what word goes with in? Taken in. More energy is taken in. There's in, I've used in. Breaking bonds. More energy is taken in, breaking bonds, than is given out, making bonds. Done. That's all you've got to do. You've got to know these two variations on that. Alright, so I'm just going to do the exothermic again. BB in, MB out. So how does the exothermic one? So I'll go, this side is more energy is given out, making bonds. What a scruffy man I am. More energy is given out, making bonds, than taken in, breaking bonds. Alright? If you sit through this video and go, yeah, I get that, and never actually write it, I promise you'll lose marks in the exam, because that's worth 3, that's worth 3. Alright? You drop 3 marks because you just wishy-washy get it wrong. If you don't get what I'm doing here, you're gonna, you kick yourself, because you won't get your 9, you'll get an 8, or you won't get an 8, you'll get a 7. Alright, learn that for me, thank you. Alright, the calculation side of this is relatively straightforward, but it is riddled with sort of pitfalls, things you can get wrong. So I'm going to quickly just go through some of these. There was a mistake on one of these, somebody told me on email very kindly. As I'm saying, I can't find my answers, so that's really annoying. I hate just the mess in my house. You've seen my lab, haven't you? So, you know, same deal. My wife gets very frustrated with me. Okay. So the way that this works then, as I'm sure you know, you've watched the videos, what you've got to do in these is you've got to work out the energy change when 2 hydrogens and an oxygen makes 2 H2O, and you've got to pick the bond energies from this diagram. So, what we're looking at here then, if you've got, how do people generally like to do it? What people like to do is they work out the bonds broken and then the bonds made, or making bonds on this side. So if you work out how many bonds were broken, or the energy required, to break the bonds, the energy required to break the bonds, what you've got is you've got 2 HH bonds to break. So you've got an HH and an HH bond to break, and you've got one of them and another one of them, because there's another one there. And you've also got an O double bond O to break. So you've got an O double bond O. And I really like this idea of just ticking through the bonds as you've used them, and ticking through the number if you spotted it. And then the bonds you're going to make 2 lots of H2O. So I'm going to draw that out again here. 2 lots of H2O means that you will make 1, 2, 3, 4 OHs. So OHs, OH, so I should have drawn that out in full. OH, OH, or you could have just written OH times 4. You then look at the table. So how much energy does it take to break an HH bond? Well, 436. So you're going to have to break 2 of them. So you're going to have to put in 436, 436. A double bond is stronger than a single bond, and 498. This is the total amount of energy that you're going to have to put in to break these bonds. All right, now I'm just going to pause the video. You won't notice because it'll be seamless after this, but I'm just going to get my calculator on my laptop. Alright, so I've just added them on my calculator, 1370. So this is the amount of energy that you're going to put in. So if we had our reactants there, you've got to put in, to this side of the curve, the activation energy curve, 1370 is the amount of energy bond breaking in that you've got to put in. Alright, I'm now going to work out the other side, which is 4 lots of OH, which is, looking at the table, where are you? 463. 463 times 4. Alright, that's you, and you. So I'm just going to do that. I'm going to tap loudly on my calculator so you can hear me doing it. 463 times 4. 1852. So that's the amount of energy released. You can see that's a bigger number than 1370. So 1852 will take you lower down there. This side is 1852. So you can see from these two numbers that more energy is released making bonds than was taken in breaking bonds. All right, the final step with any of these is you do bonds broken minus bonds made. So you do bonds broken minus bonds made. The number that you could work out first, bonds broken minus this. So it's 1370, which is the energy you put in, minus 1852. So you'll know that this is going to give you a negative number, which is good because you know that it's released energy. So 1370 minus 1852. So this difference here is minus 482. Minus 482. Now it's an incredibly simple idea, but here are the pitfalls. High functioning people, good at maths like a lot of you, often make mistakes on these because you do things, strange things, like you read the number 463, but you write the number 436. Anybody, has that happened to anybody when you've done these? All right, that happens. It's known as a transfer error, and it's actually very common amongst very intelligent individuals. I do it a lot. So watch out for that. Other big pitfalls is where you see a number 2 in front of it, you don't realise. So instead of saying you've got to break 1, 2, 3, 4 C double bond O's here, you'll only do breaking 2 of them. All right, now I'm going to be speaking to a lot of you anyway very soon, next week. So I hope you got on fine with that. The feedback so far is that everybody's done okay, those who've responded. One of these is incorrect though, the answer that you've got on your answer sheet. I would be able to tell you which one, but I can't find my answers. So I hope you found them okay. Just see, is there anything weird? Oh yeah, other little things. Right, I'll look at question 4. This might have happened to some of you. Quite often on a diagram like this, people will go, I'm going to break this one, this one, this one, this one, this one, this one, this one. And they tend to miss, it's an odd thing, they tend to miss the bond between the C and the C. And I don't know why that is, but it happens quite a lot. So it's really, really easy to do right. But from years of experience, it's really, really common for people to get it wrong and get really frustrated because you know it's simple. You just can't get the right answer. It rewards care. And that's why I have to do this sort of ticking off all the bonds to make sure I don't miss one. You can imagine I wouldn't be very good at this, though, can you? Just rushing too much and missing bonds. So that's the only way that you're really going to muck up. In an exam, if you just got one, I would just draw a line down there and work out bonds broken, and then on this side of the line I would do bonds made. I would list it out like this. I'd break in a CH. How many CH have I got? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 lots of CH. I'd do that calculation. 6 times 412. Put that into my calculator. I've got a C single bond C there, a CC, which is 348. And I've got a C double bond C there, which is 612. I'm just going to add them up. And then on the bonds made side, I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 CHs. And I've also got 1, 2 CCs. 2 CCs. Alright, and what would they be? 8 times 412 and 2 times 348. You'd add them up, a number there, a number there. So this is this one, and then you go this number minus this number. Gone off the screen again. Okay. I don't think you should find that particularly difficult. Okay, I will say one more thing before I finish this little video. Sometimes they can be sneaky, and I don't know if I gave you one of the sneaky ones in your questions. No. Alright. there are some really good questions, right, where they will give you the overall change. They will give you all of the energies that you need, but they might not give you one bond energy, and they can ask you using the overall energy change to work out the missing bond energy. I'll find one of them for you next week to give you. So I'm probably going to just give you some more questions like this next week. But they're really nice, and you know that the higher level, and you'll be fine with them. Okie dokes. Right, I think that's the end of that video. Final one will be me going through the exam questions.